The main purpose of this video is to educate and as well as serve as a challenge to students. It will make you master the concept of integration to your fingertips. Now, these questions cover a range of techniques, including basic antiderivatives, substitution, integration by parts, partial fractions, area of volume on the curves. Now, grab a piece of paper and a pen and let's get started. But then, quick question, why did the math book look so sad? Well, it had way too many problems. Okay, let's get started. So before we get into the 4 sections of this video, let's take a look at how basic integration works. We're going to calculate the integral of x with respect to x. So we're going to take a look at the power of x, which is 1, add 1 to it, and then divide by the new power of x, just like so. So the new power of x would be 2, and then our final value will be x squared over 2 plus a c, because this is an indefinite integral. So let's take, for example, the derivative of x squared over 2 plus 3. You would see that our answer would just be x squared. If you change that value of 3 to 5, we'll still have x. So that goes to show that the c here can be any of these values. Okay, question number 1. We're going to calculate the integral of x to the power 4 plus 3, x squared plus 5 with respect to x. So again, we take a look at the powers of x, which are 4, 2, and 0. Add 1 to them and divide by the new powers of x. Alright, then this would be x to the power 4 plus 1 over 4 plus 1, and so on. Okay, our new powers would be x to the power 5 over 5, and then 3x to the power 3 over 3 plus 5x plus the c, of course, never forget the c. Question number 2. Calculate the integral of e to the power mx plus n with respect to x, where m and n are constants. So with this, you need to know the notion of the integral of e to the power x being just e to the power x. So if you can change the value of the power to a u, which is basically u substitution, we'll be able to find the integral of e to the power u. So we're going to let u be equal to mx plus n. Then the derivative of that is m. Then we substitute back the values into the original equation, and we will have e to the power u du over m. So therefore, integral of e to the power u would still stay the same as e to the power u divided by m. Then we replace back the value of u, and then we get our final answer, e to the power mx plus n over m plus the c. Okay, question 3 is a definite integral with limits from -3 to 4. So we have to integrate 6x squared plus 2x plus 3. Again, we would have to add the powers by 1 and divide by the new powers of x. So this would be 6x to the power 2 plus 1 over 3, 2x plus 1, 2x to the power 1 plus 1 over 2, and 3x to the power 0 plus 1 over 3, with limits 4 and -3. Now, after we work out the integral, we are going to have to substitute the values of 4 and -3, but then we would have to subtract the value that we get from substituting -3 from that of 4. So this is our integral. We now substitute the values of 4 and -3 respectively, and then we work out our final answer, which is 210. Question number 4. We have the integral of 10 over the cube root of x squared, which we can rewrite as 10 over x squared to the power 1/3. Then we are going to use the notion of inverse indices, and then we rewrite this as 10x to the power -2/3. Now it's easier to integrate because you can see the power of x, so we're going to have to add 1 to that power. So then we would get 10x to the power 1/3 over 1/3. And then if we simplify the fractions, we'll get 15x to the power 1/3. Okay, next question, number 5. Integral of x squared minus 1 over x plus 1. So we notice that the numerator can be rewritten as the difference of two squares, which would be x plus 1 times x minus 1. Then x plus 1 would cancel out, leaving us with the integral of x minus 1. The integral of x minus 1 is x squared minus x plus the c, and that would be our final answer. Question number 6. We have the integral of cos to the power 4 of x sine x dx from 0 to half pi. Okay, so for us to integrate this, we have to use u substitution and replace the one with the greater power with u. So the cos is the one we'll replace in this case. So we let u be equal to cos x, so that is derivative. Du by dx is equal to sine x. Now we're going to have to make dx the subject of the formula, and then we replace that into our original equation. So we substitute the value of u and dx as well, and then we would get u to the power 4 sine x du over sine x. Sine x cancels out, and we have u to the power 4. So we need to integrate u to the power 4 with respect to u, and that gives us u to the power 5 over 5. Okay, u is cos x, so we're going to have to replace that back into our equation, and we have our final answer as cos to the power 5 x over 5. The limits are 0 to half pi, so we substitute the limits again and we subtract. So this will be basically cos to the power 5 of 90 degrees minus cos to the power 5 of 0 all over 5, and our final answer is negative 1/5. Question number 7. We have the integral of cos 4x dx. So with this, you have to know that the integral of cos x is simply sine x. So we'll have to replace the 4x with a different variable u, so that we can easily integrate cos u as a sine u. So we let u be equal to 4x, then definitely dx equals to du over 4. Now we'll have to replace this into the original equation, and then this gives us the integral of cos u du over 4. We take out the constant, and then we integrate cos u. This would give us 1/4 sine u plus c, and putting back the value of u in there, we would have 1/4 sine 4x plus c. Question number 8. We have the integral of x squared, square root of 1 plus x cubed. So we can see that the derivative of what's inside the square root is actually x squared, which we already have on the side as x squared itself. So if we let u to be what's on the inside, 1 plus x cubed, then we can replace each of these values, and we get the integral of x squared, square root of u du over x squared. Now the x squares will cancel out, and we have the integral of just the square root of u. The square root of u is the same as u to the power half, so we integrate that by adding 1 to the power, and then this should give us u to the power 3 over 2 over 3 over 2. Simplifying the fraction, we should get 2/3 the square root of u to the power 3. But then we need to replace back our original value of u, which is 1 plus x cubed. And then we would have our final answer. Question number 9. We have the integral from from e to e squared of 1 over x ln x all squared dx. So we can use the notion of antiderivatives or u substitution. So if we just let u to be ln x, the derivative of u is 1 over x dx. So then we substitute that into the original equation, and then we would have the integral of 1 over u squared. Take the inverse of that. It means we're trying to find the inverse of the integral of u to the power negative 2. This would be u to the power negative 1 over negative 1. Now, we substitute u back into our final answer and we get negative 1 over natural log of x. Putting in our limits, which are e squared and e, we would have negative 1 over 2 plus 1, which is equal to a half. So our final question number 10, a half. Show that the integral of ax plus b to the power 12 dx is equal to ax plus b to the power 13 over 13a plus c, where a, b are constants. So if ax plus b is equal to u once again, we would have the derivative of u being equal to a. We're going to substitute this into our original equation and we have integral of u to the power 12 times du over a. Now the final answer will be 1 over a u to the power 13 over 13 plus c, and if we put back the value of u, we will get ax plus b to the power 13 over 13a plus c, just as required. Question number 11. We have the integral from 0 to 1, x plus 1 over x. Well, dx, of course, with respect to x. So this question is a little bit tricky. Don't forget that the integral of 1 over x would not be the same as the integral of x to the power minus 1. You have to remember that the derivative of ln x is 1 over x. So if we integrate 1 over x, we're basically doing the reverse, right? So let's go ahead and separate the two sections into the integral of x and integral of 1 over x. And then the integral of x would be x squared over 2, and the integral of 1 over x would be ln of x, just like I said. Now we need to substitute the limits of 0 and 1 so that we can subtract. And if we do that, we're going to have a value of half plus 0, which is basically half. Question number 12. We have the integral of x squared plus 3x plus 4 over x to the power 4 from 0.5 to 2. So we need to separate each of these terms and give them a denominator of x to the power 4, so that we're going to have x squared over x to the power 4 plus 3x over x to the power 4 plus 4 over x to the power of 4. Now we simplify using the rule of indices and we get what we have as 1 over x squared plus 3 over x cubed plus 4 over x to the power 4. Alright then, using the notion of negative indices, we can see that the powers of each of them are negative 2, negative 3, and negative 4 respectively. Integrating that is simply adding 1 to each of those powers, right? And then dividing by the new power. This will give us x to the power minus 1 plus 3x to the power negative 2 plus 4x to the power negative 3. Substituting the limits, which are 2 and 0.5, we would get our final answer, which is negative 44.25. Question number 13, we have the integral of t cubed minus 3 to the power 5 over t to the power 5 dt. So again, we are going to put each of the terms having a denominator of t to the power 5, just like this. Then we use the rule of indices to simplify each variable, and then we get t to the power minus 2 minus 3 t to the power 0, which is still a 3. If we integrate this, we should have t to the power minus 1 over minus 1 and 3t. This would give us negative t to the power negative 1 minus 3t plus a c. And our final answer will be negative 1 over t minus 3t plus c. Question 14. We have the integral of 3x e to the power x dx. So for this question, we are going to use integration by parts. So if we recall the formula, we know that the integral of u dv should be equal to uv minus the integral of v du. So in order for you to choose your u and your v, you have to make sure u is the one which is easily differentiable, and it also helps the power of x reduce. So in this case, we take 3x as u, because if you differentiate that, the power of x will reduce and we'll just have a 3 left. So u being equal to 3x and dv being equal to e to the power x, this would give us du by dx, which is 3, and the integral of e to the power x, which is just e to the power x plus the c, right? Substitute into our formula, we should get 3x brackets e to the power x plus c minus integral of 3 times e to the power x plus c. If we disregard the constant, which is 3, it means we just need to integrate e to the power x, and that will give us e to the power x again. Now, multiply by the 3, we'll have 3 e to the power x plus a c, because if you multiply 3 by a constant, it will still give us another constant. Now, if we regroup the values that we have got, we would have the integral of u dv being equal to 3x times e to the power x plus c minus 3e to the power x plus c. And simplifying that, we should have 3x minus 3 e to the power x plus c. Question number 15. So we have the integral of x cos 4x dx. So we are going to take u to be x, since it's easily differentiable. So if u is x, that means dv would be cos 4x. Now du by dx is just 1, and then v will be the integral of cos 4x, which is 1/4 sine 4x, which we had seen in a previous question. So now we substitute the values of v and du into the formula for integration by parts, and we should get this. So now we're going to focus on the right hand side of the equation to integrate 1/4 sine of 4x. So we take out the constant, and if we integrate sine of 4x, once again, we should get negative 1/4 cos 4x. Okay, simplifying that, we would have 1/16 cos 4x, and then our final answer would be 1/4 sine 4x plus 1/16 cos of 4x, just as in question 16. We have sine square x cos x dx. Okay, to integrate this, we can let u be equal to the sine x, hence du by dx is cos x. Now, since du is equal to cos x dx, we can replace that, and as well as the value of u, so we get the integral of u squared du. Integral of u squared would just be u cubed over 3, and then replace back the value of of u, we get sine cube of x over 3 plus a c. Okay, that was an easy one. Question 17, we have the integral of x squared with x dx, where f of 1 being equal to 2. Okay, that's an interesting annotation. So we need to understand that when x is equal to 1, f of x will be equal to 2. Okay, so we are going to rewrite the equation as x squared times x to the power of half, so that it's easy to see the indices and add them up, and that gives us x to the power 3 over 2. And now we integrate with respect to x, and we simplify the fraction. That will give us 2/5 x to the power of 5 over 2 plus c. Now, if f of x is equal to our final answer, then when x is equal to 1, f of 1 has to be 2. So we substitute the 1 and a 2 in there so that we can find the value of c. So 2 would be equal to 2 times 1 to the power of 5 over 2 divided by 5 plus c. And if we work out the value of c, which is 2 minus 2/5, we should get 8 over 5. In that case, our final integral would be 2x to the power of 5 over 2 over 5 plus 8/5. Question number 18. We have to calculate the integral of 2 over x squared plus 6x minus 7. So here we have to use the notion of partial fractions. For the denominator, we can see that the quadratic can be factorized into two separate parts. So we find two numbers that will multiply to give us -7 and add to give us 6, and that would be -1 and 7. Now we replace that into the equation and we find the partial fractions, which would be a over x minus 1 plus b over x plus 7. Okay, so we are going to work just with the numerators, which would be 2 equal to a times x plus 7 plus b into x minus 1. So if x is equal to 1, then a would be 1/4. And okay, so now we need to work out the value of b by substituting x equal to -7 so that it eliminates the a. That would give us 2 equal to 0 plus b times -7 minus 1 plus a 0. Hence b is -1/4. Okay, we can now substitute this into our original equation as partial fraction. So this will be the integral of 1/4 times 1 over x minus 1 minus 1/4 times 1 over x plus 7. So we substitute the denominators for u. Okay, if we let u be equal to x minus 1, du by dx is just the 1, and then the integral will be natural log of x minus 1. And then for 1 over x plus 7, keep in mind we're going to have the same thing. So this will just be natural log of x plus 7. So our final answer would be 1/4 natural log of x minus 1 minus natural log of x plus 7. Keep in mind that absolute value is important. Then we simplify this using the rule of logarithms. This would be 1/4 natural log of x minus 1 over x plus 7. Question number 19. We have the integral of x minus 2 over the square root of x minus 4. So we're going to let u be equal to x minus 4 so that du by dx would just be 1, and hence du is equal to dx. But then we need to make x the subject of the formula so that we can substitute it back into the original equation. So this method is called back substitution. Here we would replace x with u plus 4 so that we get u plus 4 minus 2 over square root of u. Okay, this simplifies to the integral of u plus 2 over the square root of u, And then now we're going to give each of these the denominator of square root of u. Then we use the law of indices to simplify each of these, in which case we would have the integral of u to the power 1 minus a half plus 2 u to the power minus a half. So we have to integrate u to the power half plus 2 u to the power minus half. This would give us u to the power 3 over 2 over 3 over 2 plus 2u to the power half over half plus c. And then if we just manipulate the fractions, we will get 2/3 u to the power 3 over 2 plus 4u to the power half plus c. And that would be our final answer, which you can actually rewrite as seen on the screen. Question number 20, we have the integral of e to the power x plus over 1 plus e to the power x, pardon me. Okay, for us to integrate this, we will let the denominator be u. So if u is 1 plus e to the power x, therefore du by dx is still e to the power x. Okay, we can see that we are using the notion of basic antiderivatives here. So in this case, if we substitute each of the values, the e to the power x would cancel out and we have just 1 over u left. The integral of 1 over u, once again, is natural log of u, and then we replace u again and we have our final answer, ln of 1 plus e to the power x plus c. There we go. Question number 21, integral of tan x. Tan x can be written as sine over cos x, so we can replace the denominator, which is cos x, right, with the u. If u is cos x, the derivative is negative sine x, and then dx equals to negative du over sine x. Replacing this into our original equation, which has been highlighted below, you would see that this is the integral of sine x over cos x times negative du over sine x. Sine x actually cancels out and we have the integral of negative 1 over u, and our final answer, which is negative natural log of cos x plus c. Question 22. Find the area of the region bounded by this curve and the y-axis. So we need to recall that the area of a curve bounded by the y-axis is the integral from a to b of x dy, since it's the values of y that are changing and we are integrating with respect to the y-axis. So we need to first of all make x the subject of the formula so that we can substitute into our integral formula. Now if y is equal to square root of x minus 2, this implies that x would just be y squared plus 2, right? Substituting that, we are going to have the integral of y squared plus 2 dy, which is pretty simple. This will give us y cubed plus 2y, and we need to substitute 0 to 2. Okay, substituting 2, you have 2 cubed over 3 plus 2 times 2. But if you substitute 0, everything's going to cancel down to 0, right? Okay, working this out, you'll have 8 over 3 plus a 4, and this will give us 20 over 3 square units. Question 23. We need to find the area under the curve y equal to 4x cubed plus 4 between x equal to negative 1 and x equal to 2. So we're basically just integrating this from negative 1 to 2. Okay, so we have the integral of 4x cubed plus 4. Again, we have the powers, which are 3 and 0. We add 1 to those and divide by the new powers, and we get 4x to the power 4 over 4 plus 4x. Substituting the limits, we should get this value right here, and then when we work it out, our final result would be 27. Question number 24. We're going to use substitution x equal to tan u to show that 1 over 1 plus x squared dx is equal to tan inverse of x plus c. Okay, let's go ahead. If x is equal to tan u, right, it means that u is equal to tan inverse of x. But then what will be dx by du? So if we differentiate tan u, we should get sec square u, okay? So we substitute this back into our original equation. This would be 1 over tan 1 plus tan squared u times sec squared u du. And remember that 1 plus tan squared u is an identity, it's a trigonometric identity, which you replace with sec squared u, just like this, and the sec squared u cancels out, and we integrate 1 with respect to u, and that will be u plus a c. But then u is tan inverse of x, so our final answer would be tan inverse of x plus c. Question 25. By using the substitution u equal to 2x minus 2, or otherwise find the integral of 2x over 2x minus u all squared. Now, if u is equal to 2x minus 2, therefore 2x will be equal to u plus 2. And then the derivative of u with respect to x is just the 2, right? So remember that in the original equation or expression, there's a 2x in the numerator. So we're going to replace that numerator with u plus 2. So we're going to use back substitution for this question. And in this case, we would have the integral to be u plus 2 over u squared. Then we give each of them a denominator of u squared once again, and we have the integral of 1 over u plus 2u to the power minus 2. Integrating this, we should have the natural log of u plus 2 to the power minus 1 over minus 1 plus the c, of course. So our final answer will be natural log of u plus, okay, I should have simplified this as minus 2u to the power minus 1 plus c. Let's take a look at the intermediate questions. So question number 26 says we should integrate from negative infinity to infinity the value 1 over 9x squared plus 4 dx. So we can see that 9 and 4 are perfect squares, right? And so is x squared. So if we can group those all together into one and then square it all, then we'll be able to get that particular value be equal to tan x. That's how we see things. So let's start off by factorizing the 4. We get 1 over 4 brackets 9x squared over 4 plus 1, right? So we're going to rewrite this as 1 over 3x over 2 all squared plus 1, just like I said. Now we can let 3x over 2 be equal to tan x, or tan u, pardon me. In this case, we can differentiate u with respect to x, and we can see that the derivative of tan u with respect to x is just 3 over 2. And the derivative of tan u is sec squared u, so this would be sec squared u du being equal to 3 over 2 dx. Okay, now we're going to change the variable. Sorry, I should have put the du over there. We're changing the variable, and we need to replace the dx into our equation. This would be 1/4 1 over tan squared u plus 1 times dx, which is 2/3 sec squared u du. Now the sec squared u's would cancel out, and we are going to be left with just the 2/3, just like so, which we can actually take out of the brackets. And then we integrate just the value 1. We would have 1/6. If you simplify the fraction on the outside, you get 1/6 of u from negative infinity to positive infinity. If we replace back our value of u, we should get 1/6 tan inverse of x from negative infinity to infinity. Now, here's the fun part. We need to find the limit of this function as it tends to infinity and negative infinity. So if we use the graph of tan x, we'll see that as it approaches in positive infinity, it gets to positive pi over 2. And if it approaches negative infinity, it gets to negative pi over 2. And then if we subtract both our answers, it will just give us 1/6 of pi over 2 minus pi over 2, which is just 1/6 of pi. Question 27, we have to find the integral of k cubed x cubed over a squared minus a to the power 4 x to the power 4 dx, where k and a are constants. If you look keenly, we will see that the denominator would have a derivative of x cubed. So it's easier to just let everything that we have in the square root be equal to u, so that when we differentiate it, it's going to cancel out with the x cubed, which is in the numerator. So we let u to be a squared minus a to the power 4, differentiate it. We'll have negative 4a to the power 4x cubed. Now we are going to replace each of these values into our original equation. And then we have the integral of k cubed x cubed over square root of u and du over negative 4. You know, all of that. It has been highlighted. Okay. We're going to take out the constants, cancel out the x cubed, and we have the integral of 1 over square root of u, which is the same as the integral of u to the power minus half. And then if we add 1 to that power and divide by the new power, we'll get u to the power half over half plus c. Simplifying this, you get 2u to the power half plus c. Now let's not forget our constants, which were outside, k cubed and the rest of it. So this would be k cubed over negative 4 a to the power 4 times 2 a squared minus a to the power 4 x to the power 4, which is basically the value of u which has been replaced. But that's fine. Question number 28. We have the integral of square root of x e to the power 2x squared x. So if we take a look at the power 2x squared of x, we can see that they have common bases. We can simplify using the law of indices. So if we let e to the power 2x squared of x be equal to u, then we simplify it. It will be 1 plus a half, which is basically 3 over 2. So that will be e to the power 2x to the power 3 over 2. Now, if we differentiate this, we would have 3x to the power half e to the power 2x to the power 3 over 2, which is basically 3 square root x e to the power 2x square root x. Like I said, I can explain differentiation in another video. So now we replace this value back into the original equation. We would see that the integral of square root of x e to the power 2x squared x dx would be equal to integral of square root x e to the power 2x squared x du all over 3 root x e to the power 2x root x. Now it's going to cancel out nice and neatly. And then we're just going to have 1 over 3 left. So the integral of 1 over 3 is 1 over 3 u plus c Then we replace back the value of u. This will give us 1/3 e to the power 2x square root x plus c. Question 29. We have the integral of x e to the power 2x plus 1 dx. So if we let u be equal to 2x plus 1, this would imply du by dx is equal to 2. Now that would simplify the function for us, but then we'll still have x in the beginning. So I think we might need to use integration by parts. Okay, so if I replace the value of u, I'm going to have integral of x e to the power u du over 2, just like I said. And if now s is equal to x and dt is equal to e to the power u, which is integration by part, ds over dx equals to 1, and then t will equal to integral of u e to the u, which is still e to the u, right? Now substituting the formula for integration by parts, this would be st minus integral of t times ds over dx. Substituting each of those values, we'll have half times x e to the power u minus integral of e to the power u, which is still e to the power u. We are going to replace our value of u, and we get our final answer, which is half x e to the power 2x plus 1 minus e to the power 2x plus 1. Question number 30. So we have the integral of x squared over square root x minus 5 from 6 to 9. So for this question, we would need some back substitution and u substitution as well. So if we let u be what we have in the square root, right, then du by dx will just be 1, hence du equals to dx. Then the integral of the original equation would be x squared over square root of x minus 5, and we replace x in the numerator. So if x is equal to u minus 5, then x will be u minus 5 all squared. After substituting u minus 5 all squared, we use the binomial expansion of this value to give us u squared minus 10u plus 25 all over square root of u. Then again, we would separate these, with each of them having a denominator of square root of u. So this would be the integral of u squared over square root u plus 10u over square root u, and so on. Simplifying the powers of u, we would have u to the power 2 minus a half plus 10u to the power 1 minus half plus 25u to the power minus half, and then we integrate with respect to u by adding 1 to each of the powers. So we add 1 to each of these powers, and we'll have our answer as u to the power 5 over 2 over 5 over 2, 10 u to the power 3 over 2 over 3 over 2, and so on. But remember, we need to substitute 9 and 6 so that we subtract and have our final answers. Okay, if we substitute the value of u back into the final answer, remember that u was x minus 5, we will get this equation right here. And now we can finally plug in 9 and 6. If we plug in 9 and 6, we would have these values. Using our calculators, we should get 109.066. Question 31. A curve is such that dy by dx is equal to 3 root x plus 8 over x squared. Given that the point 4, 20 lies on the line, find the equation of the line of the curve, pardon me. Okay, so for us to be able to find the equation of the line, we need to integrate this function, given that integral is the opposite of differentiation. So if we have dy by dx being equal to that, then y will be equal to the integral of 3 root x plus 8 over x squared dx. So this is pretty simple. The powers of x would be half and negative 2 respectively. This would be 3x to the power half plus 8x to the power minus 2. Add 1 to the powers, divide by the new power. We're going to have 3x to the power 3 over 2 over 3 over 2 plus 8x to the power minus 1 over minus 1 plus a c, of course. And now they're telling us that the point lies on the line. It means we need to substitute these values for x and y and find the constant term. Okay, so when x is 4, y is 20. Substitute this into the equation, and we have 20 equal to 2 times 4, all of this plus c. And then if we are able to simplify this value using our calculators, we should be able to get the value of c, which is 6. Case, our answer would be our integral plus the value 6, which we got. There we go. Number 32. 20x plus 7 to the power 2024. So we can see that the derivative of the 1 on the inside, it would just be 50. So we can see that the derivative of the expression on the inside would just be 50. So we let the expression be equal to u. Du by dx equals 50. That means the integral of 50x plus 7 to the power 2024 would be u to the power 2024 times du over 50. Take out the constant, then add 1 to the power of u and divide all through by that power. So this will be u to the power 2025 over 2025 times 150. Replace the value of u back into our final equation. This would give us 150 times 50x plus 7 to the power 2025 over 2025 plus c. 33, we have the integral of cos x minus sin x plus cos x. Observe that the derivative of the denominator is equal to the numerator, the value in the numerator. So if we let the denominator sin x plus cos x be equal to u, or we just see that the derivative is cos x minus sin x, we can then highlight this and then replace all of the numerator, including the dx, with just the derivative of sin x plus cos x. Now, remember that the integral of f prime of x is equal to f of x itself, and also the integral of f prime of x over f of x is the natural log of f of x. So we would use this notion, and our final answer would be the natural log of what's in the denominator, which is sin x plus cos x. Answer would be natural log of sin x plus cos x plus c. Question number 34. We have the integral of sin x over 1 plus cos x dx. Of the denominator, except for the fact that you would have a negative. So let's see. The derivative of cos is actually negative sin x. So if we actually group them together, sin x and dx together, we would see that it's f prime of x in the denominator. So if we attach a negative to sin x, we have to replace it with a negative on the outside so that we don't alter the original question. This would be the negative of the integral of negative sin x dx. So once again, we use the notion that we used in the previous question, and this will give us negative natural log of 1 plus cos x, and as always, we need to add the c to our final answer. 35. Integral of x cos x will be equal to x, and cos x be equal to dv. We use integration by parts. This would be du by dx, which is 1, and dv equal to sine x. Now, integral of u dv would be equal to x sine x minus the integral of 1 times x. Integral of sine x right here would just be negative cos x. And if we simplify this with the negatives on the outside, we should have a plus. So our final answer will be x sine x plus cos x plus a c. 36. We have the integral of 1 over x squared plus 3x plus 2 dx. So here we need to use partial fractions. But first we factorize the denominator. We find two numbers that will multiply gives us 2. When we add, it gives us 3. That will be 2 and 1. So it will be the integral of over x plus 1 times x plus 2. Partial fractions, since the denominators, or let's say the factors, each have just a degree of 1 as the power of x, it means we need to just use a and b for the two separate factors. If it were x squared, then you have to use ax plus b, you get. So here we'll focus on the numerator, and we use elimination method to work out a and b. So when x is equal to negative 2, we get the value of b, which is minus 1. And when x is minus 1, we get a, which is equal to 1. Substitute back those into the equation, and we can see that each of these result of natural logs. So this will be the natural log of the magnitude of x plus 1 minus natural log of x plus 2. Using the law of logarithms, this would give us natural log of x minus 1 over x plus 2. Question 37, we're going to find the integral of 1 over the cube root of x minus 9 dx. So we're going to use substitution for this question. We're going to let the denominator be equal to u. So if the denominator is u, then we can differentiate this with respect to x, and we get 1/3 of x to the power 1/3 minus 1. Then we go ahead and simplify this fraction so that we get 1/3 cube root of x all squared. Replacing the value of u into our original equation, we would have the integral of 1 over u dx, but we need to make the x the subject of the formula as always. So we cross multiply over here, then we're going to get 3 cube root of x all squared du. Okay, we substitute that into our formula, but then we still have x, so we need to get rid of the x so that everything would be a variable of u. In this case, we'll make the cube root of x the subject of the formula, and it's going to be u plus 9. When we substitute that, we're going to have 3u plus 9 all squared. Expand the bracket using binomial expansion, and then substitute that back into our equation. Next, we are going to integrate with respect to u, but then look at the denominator, it's u. So we simplify each of these terms by dividing by u. Integrating this by adding 1 to the powers and dividing by the new powers, we're going to get u squared over 2 plus 18u minus 81 natural log of u, since this one has a 1 over u, plus the c of course. Okay, so we are going to substitute back the value of u to get our final answer, which is this cumbersome value you see on the screen. Okay, moving on to question number 38. So this question requires partial fractions and a difficult partial fraction. So we can let A and B be the variables we use, and then we focus just on the numerator and then the elimination method as always. So I'm not going to go very much in depth with this, but if we have x equal to -2, we'll get the value of A, which is 12/19. And we have x equal to -40. We will have the value of B, which is 61,586/19. Substitute these values back into the original equation. This should give us the integral of 12/x plus 2 plus 61,586/x plus 40. And as always, this will give us natural logs. So we have 119, the natural log of x plus 2, plus 61,586 natural log of x plus 40. And we can rewrite this as the power. So this will be 119x plus 2 plus natural log of x plus 40 raised to the power 61,586. Question 39. We have the integral from 0 to 0.5 pi of 3x sine 2x. We can use integration by parts. So we let u be equal to 3x and dv equals to sine 2x. So du by dx is 3 and v will be -half cos 2x. Substitute this into the formula. We would get 3x times -half cos 2x minus integral of 3 times -half cos 2x. So we'll just focus on this right hand side of the equation. To integrate cos 2x, that'll be half sine 2x, right? If we now substitute this back into the equation, we would have -3/2x cos 2x plus 3/2 half cos 2x. If you remember, you check out question number 7 where we integrated sine 2x and cos 2x. Okay, now we can go ahead and plug in our limits. So we have the integral from 0 to 0.5 pi. So if we plug in 0.5 pi minus 0 itself into each of the values of x, we will get -3/2 times 0.5 pi cos 2 times 0.5 pi plus 3/4 sine 2 times 0.5 pi. This should give us 3/4 pi. Okay, if we substitute 0, we should get a value of 0. And then if we minus both values, we will still get 3/4 pi as our final answer. Question number 40. We have the integral of x e to the power ax. Okay, so we're going to let u to be x and e to the power ax to be dv so that we can integrate it later. Okay, this would be du by dx, which is 1, and then v would be the integral of e to the power ax, which is 1/a e to the power ax. So the explanation is, if t is equal to ax, then dt by dx is equal to a, and dx is equal to dt over a. Obviously, we use a change of variables, and we will get integral of e to the power t dt over a, and finally 1/a e to the power ax as v, right? Now we're going to substitute into the formula, and we should get our answer: x times 1/a e to the power ax minus integral of 1/a e to the power ax dx. Okay, if we're focusing just on the right hand side of the equation, which is the integral of e to the power ax, we would see that the 1/a would multiply each other to give 1/a squared e to the power ax, right? Then we substitute back, and we'll get 1/a x e to the power ax minus 1/a squared e to the power x. And our final answer should include a c. Question 41. We have the integral of x squared over x squared plus 1. So the numerator and the denominators have the same degrees of x. So you can use long division to simplify this, or you cannot use partial fractions. So you can use some logics and say that this is the same as x squared plus 1 minus 1 over x squared plus 1. Then you separate each of them so that it cancels out. You separate the numerator as x squared plus 1 and a minus 1. So the first part of the expression will just be 1, and the second part will be 1 over x squared plus 1. So now you can integrate 1 dx and 1 over x squared plus 1. Integrating the second part, if you recall, this is actually tan inverse of x. So let's see, if you let x to be tan u, derivative of x is sec squared u. So you would have 1 over tan squared u plus 1, sec squared u du, which cancel out. And then you have the integral of du equal to x minus u, right? U is actually tan inverse of x. So if we replace all of that, we would have our final answer as x minus arc tan x, or tan inverse of x. Question 42, we have the integral of 3x times the square root of x minus 1. We need to let u to be the one which is easily differentiable. In this case, we'll take 3x. And then dv would be square root of x minus 1. du by dx equals to 3, and v would be the integral of square root of x minus 1. So we can use u substitution or basic antiderivatives, where we have the integral of f prime of x and f of x. So what's on the inside, which is x minus 1, can be differentiated, and it's going to have a derivative of 1, right? So if we can include a 1 right here, we would see that f prime of x is the 1 itself. So 1 dx is f prime of x. And so we're focusing just on the x minus 1 to the power half. So we're going to treat that as an entity on its own with a power of half. And if you're integrating with the power of half, it means you need to add 1 to that power and divide by the new power, right? So this would make the integral of this be equal to 2/3 of x minus 1 to the power 3 over 2. So I basically added the power and divided by the new power. Okay, now we can go ahead and use the formula for integration by parts. We substitute it, and we should get 3x times 2/3 of x minus 1 to the power of 3 over 2 minus the integral of 3 times 2/3 of x minus 1 to the power 3 over 2. The 3's would cancel out nice and neatly. And the second part of the expression would just be the integral of 2 times x minus 1 to the power of 3 over 2. So if we want to integrate this again, we can take the constant, which is 2, outside, right? And we repeat the process as we did in the previous process, like adding 1 to the power and dividing by the new power. So if you take 2 on the outside, then we repeat the process by adding 1 to 3 over 2 plus 1 is 5 over 2, right? So we're going to get 2 times x minus 1 to the power 5 over 2 all over 5 over 2, but then that gets reversed, so it's 2 over 5, just like this, right? And if we simplify it, we will get the integral of our original question to be 2 times x minus 1 to the power 3 over 2 minus 4/5 of x minus 1 to the power 5 over 2 plus a c. Question 43, we have the integral of 1 over x ln x dx. Okay, 1 over x dx is already the derivative of ln x. So if u is ln x, then dx is 1 over x. We can even group them together like so. And then we replace ln x with u and integrate. That will give us u squared over 2. And our final answer will be ln x all squared over 2 plus c. Question 44 wants us to prove that the integral from 0 to 1 of 1 over x squared plus 1 all squared dx should be equal to cos squared theta d theta from 0 to pi over 4, and find its exact value. Okay, let's start off with the first part. So we notice that the limits change from 0 and 1 to 0 and pi over 4, right? So we can let x be equal to tan theta, since we have x squared plus 1 in the denominator. So if x is equal to tan theta, dx by d theta is sec squared theta, sorry. And the integral of our function would be equal to 1 over tan squared theta plus 1 sec squared theta d theta. And the denominator, we're going to have sec squared theta all squared, which should give us sec to the power 4 theta, right? And if we simplify this, the square will cancel out the 2, and we're going to have 1 over sec squared theta d theta. This is the same as the integral of cos squared theta d theta from 0 to 1. Now we have to replace the 0 to 1 by substituting these values into theta. For x equal to 1, theta is tan inverse of 1, which is pi over 4. Remember, we had first of all let x be tan theta, right? So in this case, it will be pi over 4 when x is 1, and for 0, we would still have a 0. Okay, now for us to find the exact value, we need to integrate from 0 to pi over 4 cos squared theta. Okay, so I think we need to use the trigonometric identity for cos squared theta. So we know that cos squared x equal to half parentheses cos 2x plus 1, right? We substitute that. Then we integrate. The integral of cos 2 theta is sine 2 theta. So we're going to have half brackets half of sine 2x plus x over 2 from 0 to pi over 4. And now we can replace our limits in our result. So this would be 1/4 sine 2 times pi over 4 plus pi over 4, and then we replace the 0 as well, and then we would have our final answer, which is 1/4 times 1 plus pi over 4. Question 45, we have the integral of x cubed plus 4x squared minus 2x minus 5 all over x squared minus 4x plus 4. So for this question, we need to use long division to simplify it, because the degree in the numerator is greater than that in the denominator. So we're going to use long division to simplify. We'll take the dividend and divide by the divisor to get x. Then we multiply x by the divisor. We'll get x cubed minus 4x squared plus 4x. Then we are going to subtract our result from the dividend. And this would give us 8x squared minus 6x minus 5. Once again, we divide this by the divisor and we should get a positive 8. Then we multiply once again to get 8x squared minus 32x plus 32. And then once we subtract these two values, we should get 26x minus 37. So we go ahead and we substitute this into our original question, just like so. And then we can actually separate these two to have different denominators. Okay, the denominator for the last term can actually change to x minus 2 all squared using factorization. Now for the third term, which is 26x over x squared minus 4x plus 4, we notice that if we differentiate the bottom, we would have 2x. But then the numerator has 26x, so we can actually rewrite this such that it has a 2x in it, which would be 13 times 2, right? And then for the last term, we also have the denominator, which is x minus 2, having a derivative of just 1, which is a constant. So we can actually rewrite both of these fractions just like this, so that the second term would have an integral of 13 natural log of what is in the denominator, while the last term would have 37 times x minus 2 to the power minus 2 plus 1, all divided by minus 2 plus 1. Okay, this will give us our final answer, which is x squared over 2 plus 8x plus 13 natural log of x squared minus 4x plus 4 plus 37 over x minus 2. Question 46. The graph of y equal to x minus 1 to the power 4 minus 1 is shown. Find the area of the shaded region by evaluating the integral from -1 to 2 of x minus 1 to the power 4 minus 1. So, first of all, we notice here that this graph is in two sections. We have section A and section B, but we have to be careful because B is in the negative region. So we need to actually separate this graph into two parts and integrate twice. When we integrate the section B part, we need to find the absolute value of the function because it's going to give us a negative value. So in that case, this would be the integral from -1 to 0 of the function plus the integral of 0 to 2 of the same function. So the integral of x minus 1 to the power 4 is equal to 1/5 times x minus 1 to the power 5 minus x from -1 to 0 plus 1/5 x minus 1 to the power 5 minus x from 0 to 2. If we substitute each of these limits, we would get -1/5 minus -32 over 5 plus 1. That's for the first part. Now, for the second part, which is in yellow, we would get 1/5 minus 2 minus -1/5, which would give us -8 over 5 square units, which I said would be negative. So then we have to find the magnitude or the absolute value of this before adding them up together. So in this case, our final answer would be 26 over 5 units plus 8 over 5 units, and that gives us 34 over 5 units. Question 47. Find the area between the curve and the x-axis y equal to x squared plus 3x between -1 and 2. Okay, so we do the same process. We separate this from -1 to 0 and 0 to 2. The integral of the function x squared plus 3x would be x cubed over 3 plus 3x squared over 2. After integrating, we substitute each of the limits before adding them up. So this would be 0 minus -1/3 plus 3 over 2, which is -7 over 6 units, and that's normal if it's negative. And for the second part, we get 8/3 plus 12 over 2, which is 52 over 6 square units. Hence, the final area would be 59 over 6 square units. Question 48. The diagram shows the graphs of y equal to 2x plus 7 and y equal to 10 minus x. Find the area of the shaded region. So here we have two straight lines. We need to take the area of the top graph minus the area of the bottom graph. So we need to determine which is which. So the top graph has positive gradient, right? So if we look at the two equations given to us, y equal to 2x plus 7 is the one with the positive gradient, and the negative gradient is the one with 10 minus x. So the integral of 2x plus 7 minus the integral of 10 minus x, and it's given between the region 2 and 4. So if we integrate 2x plus 7, we're going to have 2x squared over 2 plus 7x. And if we integrate 10 minus x, we'll have 10x minus x squared over 2. So we're going a little bit faster because I've explained all of these before. So now we substitute the limits 2 to 4. And here we would have 16 plus 28 minus 4 plus 14. This is 26 square units. Now for the second part of the graph, which is the one with the negative gradient, we substitute 4 and 2 again, and we get 14 square units. Now we subtract 26 and 14, and that will give us 12 square units. Question 49. Calculate the area the curve makes with the y-axis, given that y is equal to x minus 2 all cubed. So we need to recall that the area is equal to the integral of x dy. In this case, since we're trying to calculate the area it makes with the y-axis, so this would be integral from y1 to y2 of x dy. So we need to make x the subject by taking the cube root of y first and then adding 2. That gives us cube root of y plus 2. Now we integrate from y1 to y2, but according to the graph, we don't know what y1 is. So we need to find when x is equal to 4. When x is equal to 4, the value for y would be 8. We are integrating from 0 to 8 of the function x with respect to y. If we replace the value for x into our question, we're going to have integral of y to the power 1/3 plus integral of 2 dy. This would be y to the power 4/3 divided by 4/3 plus 2y. And if you rearrange the fraction, you have 3/4 of y to the power 4/3 from 0 to 8. Substituting the limits in each of these, we would have 12 plus 16, which is equal to 28 squared units. Question 50. Find the volume of the solid formed when the curve R is rotated completely about the x-axis. Give your answer in pi and a natural log of 2. The curve has been given with the equation y equal to 6 squared x over 3x plus 1. And we are integrating from 0 to 1. So for us to find a volume of a solid of revolution, remember you need to do the integral from x1 to x2 of pi y squared dx with respect to x. So in this case, we would have integral from 0 to 1 of pi y squared will be 6 root x over 3x plus 1, all that squared. The square will cancel out since we're squaring, and we'll get 36x over 3x minus 1 plus 1 all squared. Taking out the constants, we have the integral of x over 3x plus 1 all that squared. We can work with the partial fractions for this and then focus on the numerator. So when x will be equal to negative 1/3, b will be equal to negative 1/3, coincidentally. And then when x is equal to 0, a plus negative 1/3 is equal to 0, and hence a is equal to 1/3. We would replace each of these values for a and b and integrate the values. So we need the integral of 1/3 3x plus 1 minus 1/3 3x plus 1 all squared. If we replace u with 3x plus 1 and we factor out the 1/3, this would give us 1/3 times the integral of 1 over u minus 1 over u squared. The first part will give us a natural log, while the second part will give us u to the power negative 2 plus 1 over negative 2 plus 1. So we would have 36 pi times 1/3 natural log of u minus u to the power minus 1 plus c. Now we can substitute back the value of u as 3x plus 1, and we get 12 pi natural log of ln 3x plus 1 over 3x plus 1. If we substitute the limits as 1 and 0 in there, we're going to have 12 pi plus ln of 3 times 1, etc., etc. And we substitute 0 as well, but then natural log of 1 would be 0. So the first part of the expression would be 12 pi times natural log of 4 plus a quarter minus 12 pi times 1. Simplifying this, I'll factor out the 12 pi, and we have natural log of 4 plus 1/4 minus 1, which is negative 3/4, right? And our final answer will be 12 pi times natural log of 4 minus 3/4. Okay, let's take a quick break. Why are pirates the best at calculus? Well, because a true pirate never forgets the sea. Okay, question 51. Calculate the integral of ln x all squared dx. Okay, first of all, we are going to start by letting x to be e to the power u, such that the derivative will still be e to the power u. But if x is e to the power u, this would mean that we're going to substitute e to the power u to get ln e to the power u all squared. Now, the lateral log of e to the power u would just be u. So in that case, this would change to u all squared. Then we're going to get u squared times e to the power u du. So we've changed the variable, but now we need to use integration by parts to integrate this. So we're going to let s to be u squared and dt be equal to e to the power u. In that case, ds by dt is 2u, and then t will just be e to the power u, since when you integrate this, it still gives you e to the power u. Okay, so next up we substitute these values in the formula for integration by parts, and then here's what we get. Now we are left with the second part of the expression to work out, which is the integral of 2u e to the power u. Once again, we let s to be 2u and dt to be e to the power u. Remember, I said before in the first half of the video, you have to choose your variable in such a way that when you differentiate, its power is decreasing, right? So when you differentiate 2u again, its power will decrease and go to 0. So we have ds by dt, and we also have t equal to e to the power u. We're going to substitute these values, and this will give us the integral of u squared e to the power u as u squared e to the power u minus 2u e to the power u minus integral of 2 e to the power u. That last part or last bit is very easy to integrate. It would stay the same as 2 e to the power u. So now we are going to factorize the equation, and then we make sure that we plug in back the values of u. So remember, u would be ln x, so our final equation would be x brackets ln x all squared minus 2 ln x plus 2. Okay, question 52. We have the integral of 1 over x plus square root of x. So first we're going to let u squared be equal to x. And if u squared is x, that means the square root of x would just be a u. In that case, dx by du would be 2u. Then we go ahead and replace our values back into the original equation. And then we'll see that we're going to have 1 over u squared plus u. Okay, we can go ahead and substitute the value of the x, and this gives us 1 over u parentheses u plus 1 2u du. Now that is great because the u will actually cancel out, leaving us with 2 over u plus 1. To integrate 1 over u plus 1, like I said before, is just the natural log of what we have in the denominator. So we're going to have 2 natural log of u plus 1 plus the c. And then finally, substituting back the value of u, we'll get our final answer, which is 2 natural log of square root of x plus 1 plus the c. Next question. We have the integral of e to the power x sine x. Now this question is very interesting as we are going to get a loop. We're going to get stuck in a loop, but then I'll show you how to work through that. So let's begin by taking u as sine x and dv as e to the power x. In this case, you can take either of them as u or dv because either of them are easy to integrate or even differentiate, right? So in that case, the derivative of u would be cos x, and the integral of v would just be e to the power x. Substituting this into the formula for integration by parts, we're going to have sine x e to the power x minus integral of e to the power x cos x. And then we repeat the process again. T, but this time around with different variables, of course. Okay, so we're going to let t be equal to cos x and dv equal to e to the power x. Differentiating and integrating respectively, we're going to have dt being negative sine x and v being e to the power x. Okay, let's go ahead and substitute these right into the equation. We would have sine x e to the power x minus cos x e to the power x minus e to the power x sine x, right? That will turn into positive. Okay, expand the brackets. We would see that there are 3 negative signs in front of the integral. So there's 2 just right beside it, which has been sandwiched with the integral, and then 1 extra just before the big square bracket, giving 3 minuses, which would make a final minus, right? So we have e to the power x sine x minus e to the power x cos x minus e to the power x sine x. Okay. Here we are going to have to bring e to the power x sine x over to the left-hand side. This is what I mean by we're stuck with the loop, because if you keep on replacing u and dv, it's going to keep going on and on. So we need to bring it to the left-hand side and add them up. So both integrals will give us 2 of the integral of e to the power x sine x. And we're going to divide both sides by the 2. This is going to give us e to the power sine x minus e to the power cos x plus c, all divided by 2. Don't forget the c because, of course, we are good pirates. Okay, next question. We have the integral of 1 over square root of 4 minus x squared. If you look at this keenly, you would see that 4 is a perfect square which can be paired up or brought together with the x squared as well. So we're going to factorize the 4 on the outside. Okay, now the square root of 4 is just 2. That's going to go on the outside. You know, I always like to separate the constant from the integral itself because it doesn't really affect the integral. So we're going to have 1 over 2 somewhat at the end of the day. Okay, now, if we have 1 over x minus 2 all squared, we can let this value to be either sin x or cos x, depending on you. And then we're going to use a trigonometric identity, right? Which is cos square x plus sin square x equal to 1. And if you recall, cos square x will be equal to 1 minus sin squared x. Okay, we're going to now let x over 2 be equal to sine u, right? So let x over 2 be sine u. It means x is equal to 2 sine u. If you differentiate that, you should have 1 dx being equal to 2 cos u du. All right, then, replacing each of these into the equation, it changes the whole thing. We're going to have 1 over square root 4 minus, bracket 1 minus sine squared u times 2 cos u du. Well, if you're smart ahead, you will see that the cos is going to cancel out. Okay, so this would give us 1 over 2 square root of cos squared u. And once again, the square root of a square is just the value itself. So it's going to be 1 over 2 cos u times 2 cos u. Now the cos u cancel out nice and neatly. And we have just du to integrate, which would just be a u, of course. Now we're going to substitute u back into our answer. Now we're going to get arc sine x over 2 plus c. Okay, that was a good question. Number 55. So we have the integral from 2 to infinity of 1 over x ln x cubed dx. So if you recall, we have done a similar question in the easy or the intermediate section of this video. You can rewind if you didn't watch that part, where we saw the integral of 1 over x ln x by taking the idea that 1 over x dx is already derivative of ln x, right? Okay, but it's different this time around because we have from 2 to infinity. So we let u be equal to ln x. Derivative of ln x is 1 over x, and hence 1 over x dx is du. We go ahead and replace that in the equation with just the du. And we're going to have integral of 1 over u cubed du, which is the same as the integral of u to the power negative 3. And if you add 1 to negative 3, it should give you negative 2. So we divide all through by negative 2. Now we're going to have u to the power negative 2 over negative 2 from 2 to infinity. Went ahead to replace the value of u, which is ln x, into the equation to the power negative 2 over 2. Okay. So now we need to take the limits of this function as 1 over ln x squared tends to infinity. Now I just changed the annotation. It actually means the same thing. If you have a power of minus 2, it's the same as bringing it as a fraction, right? So we have to find this limit as it turns to infinity. So as you can see, the limits of this natural log would be 0. But let me explain. Let's say you take the natural log of 1. It's 0, right? If you take the natural log of 2, it increases to a certain number. Then if you take the natural log of, say, 9, it still increases. Now the denominator is increasing, especially as you're going to have to square it. The bigger the denominator gets, the smaller the whole expression is going to be. If you take 1 over a very large number, it's going to go closer to 0 than otherwise, if you do otherwise, right? So that's why the limit as this function turns to infinity would be 0. And now we just need to find the same function, but this time around replacing x with 2. So we're going to have negative of 0 minus ln 2 to the power minus 2 over 2. And the negative of a negative is a positive, so our final answer will be 1 over 2 ln 2. Okay, it was supposed to be ln 2 all squared. That was a slight mistake. So it's supposed to be 1 over 2 ln 2 all squared. Question 56. We have the integral of 1 over e to the power x minus e to the power minus x dx. We are going to let x be equal to the natural log of u. Now we are letting it to be the natural log of u because we want the e to the powers to cancel out. So if you have the natural log of u to be x, dx would be 1 over u du. Okay, we go ahead and substitute this into our equation, and we'll see that we have 1 over e to the power natural log of u minus e to the power minus natural log of u. So now this would be 1 over e to the power ln u minus e to the power ln 1 over u dx. Now we're going to substitute the x eventually. So this would give us 1 over u minus 1 over u times 1 over u du. For the first part of the expression, we can find the least common denominator and subtract. So this would give us 1 over u squared minus 1 over u times 1 over u du. Now for the first part of the expression again, keep in mind that the u which is at the bottom would go to the top if you simplify the fraction properly, just like this. And the u would have to cancel out eventually. This would give us the integral of u squared minus 1, which is the difference of two squares, and which is 1 over u minus 1 times u plus 1. We've seen this in the first part of this video where we have the easy questions, and this will eventually give us the final answers as natural logs. So keep in mind this expression is not being simplified. You need to find the partial fractions, which are 1 over 2 u minus 1 minus 1 over 2 u plus 1. I'm not going to explain into much detail because I have explained before. So integrating this would actually give us the natural log of u minus 1 minus the natural log of u plus 1. And then using now the rule of logarithms, we're going to have half natural log of u minus 1 over u plus 1 plus the c. Replacing the value of u again at the end of the day. Don't forget, I almost forgot. So you would have e to the power x minus 1 over e to the power x plus 1. There we go. Question 57, we have 1 over x times the square root of x plus 1. Okay, the square root of x is actually just x to the power half, right? So if we let u squared be equal to x, again, differentiate that value, you have 2u du equal to 1 dx. So I differentiated implicitly, and then we substitute this into our original equation. We're going to have 1 over u squared, parentheses, u plus 1 times 2u du. Now there's a u attached to the du, and at the bottom as well, we can cancel one of that out. This would give us 2 times the integral of 1 over u times u plus 1. Again, partial fractions, where you have a over u plus b over u plus 1, right? Okay, then we always work with the numerators for partial fractions to get each of the values. In this case, we can use elimination. So if you just let u to be 0, you will already see that b is going to cancel out, right? And it will be easy to get the value of a. So a would be 1. And then if you let u be minus 1, a would cancel out, and then b would be minus 1 as well. Substituting this into our equation, we would have 2 times the integral of 1 over u minus 1 over u plus 1, with which we'll have natural logs as our final answer for each of them. So that will be 2 times the natural log of u minus the natural log of u plus 1. This will give us 2 times the natural log of u over u plus 1, and we substitute the value of u again, and we get our final answer. Question 58, we have the integral of log x to the power 50. So for this question, it is crucial that you know the rule of indices. Otherwise, you're just gonna beat yourself up. Okay, so Keep in mind, log x to the power 50 is actually the same as 50 log of x. That makes everything look simpler, right? You just take out the constant, which is 50, and then we're going to have 50 log x over there. Now we have to know how to integrate log of x, right? We can use integration by parts here. So we know that the derivative of log x is actually 1 over x, right? Just like this. In that case, if dv is 50, it means v would be 50x. Substitute that into the formula. We're going to have 50x log x minus the integral of 50x times 1 over x. Doing so, x's will cancel out nice and neatly, and the second integral will be easy to work out, just like this. We have integral of 50, which will still be 50x. Now, the final answer would be 50x bracket log x minus 1. So we factorize the 50x at once. Okay. Question 59, we have integral of tan to the power 5x, 5 of 2x, pardon me, divided by cos squared 2x. Now, this question you need to remember that 1 over cos squared x is sec square x, right? And remember, if you integrate sec square x, you should have tan square x. But now in this case, we don't have x, we have 2x. So how about we first of all start by simplifying this whole question. We're going to let the angle, which is 2x, be equal to theta. D theta by dx will be 2. And therefore, dx will be d theta over 2. I'm going to replace that into the original question. And we're going to have tan to the power 5 theta over cos squared theta times d theta over 2. Now we can go ahead and rewrite this using the sec square annotation. So this will be the integral of tan to the power 5 theta sec squared theta d theta over 2. Okay, now finally we can isolate sec squared theta since it's the derivative of tan. So we can get rid of that tan by letting it be a different variable. So we let u be tan theta. In that case, du by d theta is sec squared theta. Then we substitute it into the equation. This equation, you see that we have u to the power of 5 times sec squared d theta, remember, is just du. So I replace that with the du. And of course, the 1 over 2 goes outside. Integral of u to the power 5 is actually easy. It's u to the power 6 over 6. So we have half of u to the power 6 over 6 plus c. Replacing the value of u once again, we would have half tan to the power 6 theta over 6, and then back again replacing theta, we have tan to the power 6 of 2x over 12 plus c. Very good question. I like this question a lot. Okay, moving on to question 16. We have 17 to the power natural log of x. Okay, there are different ways in which we can write 17, which I'm going to show you. So we can let 17 be equal to e to the power ln 17. Keep in mind, we're always trying to get rid of the natural log, so we need to use e. Okay, now in this case, if we replace 17 with that value, you see that in indices we have natural log of 17 times natural log of x. This would be interchanged just like this, so that ln of 17 goes outside because it's just a number, right? So we have now e to the power natural log of x times natural log of 17. E to the power natural log of x is just x, so we're going to have x to the power natural log of 17. Don't forget, natural log of 17 is a number, so we're going to have to add 1 to it and divide by the new value. So our answer would be x to the power natural log of 17 plus 1 over natural log of 17 plus 1. 1 is actually the same as natural log of e, isn't it? So if I rewrite this, I'm going to have x to the power natural log of 17 plus natural log of e, so that I can use the rule of logarithms, right? When you add two logarithms, you actually multiply their values. So this would be the natural log of 17 times e over the natural log of 17 times e, and we get x to the power natural log of 17e over natural log of 17e plus c. Okay, a lot of manipulations going on, but then it's good. Question 61. We have the integral of x squared over square root of 1 minus x squared dx. Okay, if we had just the bottom, it would be super easy. It would be sine squared, just like we've seen in question 50 or 51. I don't remember. Since the denominator reminds me of our trigonometric identities, we can let the x to be cos u. Now dx would be equal to negative sine u du. And then if we replace this, we'll see that the integral of x squared over 1 square root of 1 minus x squared would actually be integral of negative cos u all squared over the square root of 1 minus. So if we simplify this, the numerator would just be cos squared u, and the denominator would be sine u. Just like so. And then if we replace the value of dx, which is actually negative sine u du, which will cancel out. And then we're going to have just the integral of negative cos squared u. Okay, we have to remember that cos squared u is the same as half of 1 plus cos 2u, right? So replace that into our equation. And we integrate negative half of 1 plus cos 2u. Once we have our integral, we can now go back and replace the value of u, which is the cos inverse of x. Cos inverse of x is the same as r cos x, okay? The same thing, even if in different annotations. Okay, that's our final answer. Question number 62. We have the integral of log x to the base 100 dx. Okay, the 100 might look a bit bigger, but then that's the base. So if you remember your rules of logarithm, you would know how to change this base. We need to use the change of base rule in this case. So just recall that the log of x to the base 100 is the same as the log of x to the base 10 divided by the log of 100 to the base 10. Now, we are going to replace this into our original question, right? But you need to keep in mind that the log of 100 to base 10 is the number 2. Now we can write the question without the bases, since they are base 10, and then we need to know that log of 100 would actually be 2. If you remember question number 58, we had integrated log of x to give us x log x minus x. So we're just going to use this over here. In this case, our question would be integral of log x over 2, which I mentioned before, and our answer would just be 1 over 2 x log x minus x plus the c. Question 63. Integral of 1 over x squared plus 1. So when I see x squared plus, it gives me the idea of sec square x. But let's see how that goes. So in this case, we're going to let x be equal to tan u, right? In that case, the derivative of x would be sec squared u du. So we replace everything into the equation. This would be the integral of 1 over tan squared u plus u times sec squared u du. Now that denominator, which is tan squared u plus 1, will be sec squared u. But then the square root of sec squared is just a sec, right? So it will be sec u, and then we're going to have 1 over sec u times sec squared u, and it cancels out to give us the integral of sec u. Okay, this will be the integral of 1 over cos u. Let's see how to do this. Cos u can be written as cos u over cos u times cos u, which is cos u over cos squared u. If we recall, cos squared u can be rewritten as 1 minus sine square u, right? We're always trying to get a value for which we can substitute and then cancel out at the end of the day. So I'm going to substitute that with 1 minus sine squared u, so that I can let another variable, let's say t, to be equal to sine u, right? So if t is sine u, then dt by du is cos u. You see, it's going to already cancel out, right? Hence, we have the integral of cos u over 1 minus t squared times dt cos over cos u. That cancels out. The bottom, we have the difference of two squares, yet again, which I would not repeat over. This will give us its partial fractions as half times 1 over 1 plus t and so on. Okay then. Now that we know its partial fractions and its derivative as well, we can now replace the value of t. This would give us half natural log of the sine of tan inverse of x. So I substituted back for t and also back for the value of u to get our final answer. Okay, question 64. We have the integral of sine cube x times sine 2x dx. So remember, sine 2x is the same as 2 sine x cos x, right? Okay. If that is that, we replace into our equation. There's going to be extra sine x again. So it's going to go up to sine 4 of x, right? As always, we take the constant values out. So that we're going to have the integral of sine to the power 4x cos x dx. Now, we let u be equal to sine x. As always, we're trying to simplify. This will give us du by dx, which is cos x. Hence, we have the integral of u to the power 4 du. This would be u to the power 5 over 5, and then hence 2 sine to the power 5x over 5 plus c. Next question. Question 65. So we need to integrate the cos inverse of x dx. Okay, so we let x be equal to cos u, so that dx would be equal to negative sine u, right? Keep in mind, if x is cos u, that means u is cos inverse of x, which is the original question, okay? Don't be confused. So, in this case, we would have u times negative sine u du. What does that give us? It gives us it gives us integration by parts, not partial fractions. Okay, so we let s be u and we let dt be sine u. The derivative of s is 1, while the integral of t is negative cos of u. Okay then, replacing this into the formula for integration by parts, we should get u cos u minus sine integral of sine u only. Integral of sine u is actually easy. It's just cos of u. Now we replace back the value of u, right? Which is cos inverse of x times cos of cos inverse of x minus cos of cos inverse of x. But remember, cos of cos inverse of x is just x. So this will give us x cos inverse of x minus x plus c. There you go. Question number 66. We have the integral of 1 over x squared plus 2x plus 10 dx. So we need to factor this quadratic expression in the denominator, right? We can use factor method by finding two numbers that will multiply gives us 10 and we add it gives us 2. 5 and 2. 5 and 2 does not work. Or we can use completing the square method, which might not really work. So we are going to use a different approach for this question. We're going to rewrite 10 as 1 plus 9. And then you can see that x squared plus 2x plus 1 is actually a separate quadratic which you can simplify using completing the square method as x plus 1 all squared, right? Now we would have two squares, x plus 1 all squared and 9. 9 can be rewritten as 3 squared, and then if I factorize out the 9, or let's say the 3 squared, it's going to be 9 into x plus 1 all over 3 all squared plus 1. Taking a look, we see that x plus 1 over 3, which is in the bracket, would have a derivative of 1, right? So I can let u be equal to that expression, so that du by dx equals to 1/3. Okay, now 3 du be equal to dx, and then we're going to replace this. So let's replace the u's first. If we replace the u's, we're going to have 1 over 3 u squared plus 1. Of course, 9 is divisible by 3, so you have to just cancel out. Okay, we have 1/3 u squared plus 1, and we can see that this is the integral of tan inverse of x, right? So we've looked at the integral in the previous question, so you can go back. So it means that this would be 1/3 tan inverse of u plus c, and if we replace u once again, it will be 1/3 tan inverse of x plus 1 over 3 plus c. Question 67, we have 2 over x minus 1 all squared times x squared plus 1 dx. Now this would have to use the notion of partial fractions, but since it's slightly harder, I'm going to explain it unlike our previous questions. So I'll go into detail. When you want to work with partial fractions, you have to look at the degree of x. If it's, let's just say x squared, then the partial fraction will be 1 less than the degree. So x squared in this case will have a partial fraction of just x. So here we have x minus 1 all squared, right? This is what the partial fractions would look like, right? But then let's go back a little bit. We have x minus 1. It means we have to do a over x minus 1. But since we have a squared, it means we have a repeated root. So we have to do b over x minus 1 all squared. And then for x squared plus 1, like I said, we would have to just go 1 degree lower. It will be cx plus d. And that's how we got over here. Now we have to find the partial fractions by focusing on the numerator, right? So we simplify this by getting the common denominators, cross multiplying where we need to, and we should get something that looks like this. If you're not really sure, I can make a separate video on partial fractions for you. Okay, now we need to just eliminate the values of a, b, or c depending on our chosen values of x. If you notice, c is directly attached to x, and as well a can easily be be eliminated. If we choose x equal to 1, or even if we choose x equal to 0, we're going to eliminate either of them, right? So when x is equal to 1, we're going to have this expression, and then we simplify it. It gives us b into 1 plus 1 equal to 2, and finally b is 1. We choose another value of x again, which is 0, simplify it. Then we should get negative a plus d equal to 1. Now we can choose another value of x. We can go with x being equal to negative 1. We simplify the expression or the equation, pardon me. And we should have negative a plus d minus c equal to a 0. Now that we already know b, I substituted a value for bn, and that's how I got to this final expression. Now we also know negative a plus d from equation 1, right? Which is 1. We would substitute the 1 in there, so that will be 1 minus c equal to 0, hence c would be 1. Okay, when x is equal to 2, we simplify the equation. We will get 5a plus 5 plus 2 plus d equal to 2. Then, yet again, we substituted a value for c and simplified. And from this equation, we can see that we have a pair of simultaneous equations to work with. We can use elimination method or substitution method to find a or d. And if we do that, we're going to have a equal to 1 and d equal to 0. Now we plug back in our final answers into our original question. The first part of the question is integral of negative 1 over x minus 1, and since the numerator is the derivative of the denominator, it means our answer would be a natural log for the first part. Same for the last part, because x is a derivative of x squared plus 1. But for the middle part, it is actually a derivative, but the answer would not be a natural log. It would actually be a u to the power minus, let's say minus 1. When we integrate this, we should have negative ln x minus 1 minus 1 over x minus 1 plus ln of x squared plus 1. Use the rule of or logarithm. Then you simplify, you should get your final answer, which is natural log of x squared plus 1 over x minus 1 minus 1 over x minus 1 plus c. Wow, that is a mouthful. Okay, question 68. Integral of x e to the power negative x squared. We can see that that power is actually interesting. If you derive it or differentiate it, it will give you x. So if we let u to be that power, negative x squared, then du by dx is negative 2x. Then we substitute this back into the equation. We're going to have x e to the power negative x squared times du over 2x. And definitely the x's would cancel out, just like I said before. Okay, now we're going to have to take out the constant, which is negative 1 over 2, like this. And we have to integrate e to the power u du, easy peasy. And we will get negative e to the power u over 2 plus c. Replacing the value of u again, you have negative e to the power negative x squared over 2 plus c. Question 69. Okay, we've come to the applications of integration section, which is actually at the end of each section in this video. So here we have the diagram shows the curve y equals to x minus 2 all squared plus 1 with a minimum point at P. The point Q on the curve is such that the gradient of PQ is equal to 2. Find the area of the shaded region. Now, this question is a little hard because you need to figure out the equation of the straight line PQ. At least they've told us the gradient, so that's a good start. Recall that y is equal to x minus h all squared plus k. with the vertex being HK, right? So in this case, our vertex, which is a turning point, would just be 2, 1. Why is this important? We are going to use to find the equation of our straight line. Okay, let's go ahead. Now recall that the straight line can be written as mx plus y equal to mx plus c. And in this case, m is 2, right? So if we have a point, we have the gradient. Then we can find the c, the value of c, where it cuts the y-axis. So when x is 2, y is 1. Hence, we substitute these three values. We'll have 1 equal to 2 times 2 plus c, and hence c is minus 3. So then we get our equation of the straight line, y equal to 2x minus 3. Okay, now if these two lines intersect at P and Q, it means we can also find Q, because you know, for us to find the area of the shaded region, we need to find the integral, the definite integral from point P to point Q. We know just P, we also need to know Q. It will also intersect at point Q. So at that point, both of these equations, that is the straight line and the curve, are equal. So I'm just going to take my straight line equation and equate it to the curve, just like so, and then I'm going to work it out. So we can do some expansion using the FOR method, bringing like terms together and then simplifying. We're going to have x squared minus 6x plus 8 equal to 0. Simplifying that by factoring, we'll have x equal to 2 and 4. Okay, perfect. It means that this would cut when P is 2 and Q is 4, and those are strictly the x values, right? So we can now integrate with respect to x. Let's go ahead. For us to integrate from 2 to 4, we must take the magnitude or the absolute value of the function, which I explained before. So we subtract the bottom function from the top function. The top function is the linear equation, which is 2x minus 3, and the bottom one is the curve itself. So expanding and subtracting, we would have 2x minus 3 minus x squared minus 4x plus 4 plus 1. And when we simplify this, we have negative x squared plus 6x minus 8. Okay, integrating this is actually easy. So we would have negative x cubed over 3 plus 6x squared over 2 minus 8x from 2 to 4. Okay, we'll substitute the values of 4 and 2, simplify them with the calculator, then subtract, and we should be able to get our answer at the end of the day. Now these fractions here, notice they have the same denominator. So if you pair the like terms, it'll be easier for you to work with. So I just color coded them for you to easily see what I'm talking about. This would give us 100 over 3 square units. Question 70. Find the area bounded by the curve y equal to x e to the power negative x, the axis, the x-axis, and the lines x equal to 0 and x equal to 2. So we're going from 0 to 2 of x e to the power negative x, which is pretty simple. Integrating by parts, right? Let u be x and dv be e to the power minus x. In that case, du by dx is 1 and v is going to be negative of e to the power negative x, right? Just like this. Substituting this into our formula for integration by parts, we would have negative x e to the power negative x minus the integral from 0 to 2 of 1 times negative e to the power negative x. Okay, then the integral of negative e to the power x is going to be negative e to the power x. So negative and negative gives a positive. So we have our result with which we can substitute 0 and 2 and then subtract 0 from 2. When we substitute each of these values or numbers, we should be able at the end of the day to get negative e to the power negative 2 minus 1, which you can use your calculator to get the actual number or decimal. But we're going to leave it like that for now. Next question. Calculate the area of the shaded region. Notice that the curve intersects with the line y equal to 8. We've been given the curve, we've been given where it intersects, which is 8. But then we've not been given where the curve cuts the y-axis, which is pretty simple to do. So we have to calculate where it cuts the y-axis by substituting an x equal to 0. We let y be the function, which is already what we have. Now when x is equal to 0, y is equal to 5, right? And now x is equal to the square root of 8th root, pardon me, of y minus 5 over 3. So I'm trying to integrate the function with respect to y, means I need to change the function to make x the subject, right? So this will be the integral of x dy, like I mentioned, from 5 to 8 of the 8th root of y minus 5 over 3. Pretty simple, because the inner part of the square root would have a derivative of 1, or just a constant, right? So we can just let that inner part be u. Okay, like I said, we take the inner part being equal to u, differentiate it, it gives 1, easy peasy, substitute it in there. You're going to have the integral of u to the power 1/8. Add 1 to the 1/8 and divide by 1/8, you get 1 over 8th root of 3 times u to the power 9/8 over 9/8. So then you substitute your limits from 5 to 8. And since each of them are highlighted in different colors, it's quite easy to differentiate, right? You would have 3 to the power minus 1/8 times 3 to the power 9/8 minus 0, and that gives us the square units. Question 72. Find the area of the region bounded by the curves y1 equal to x cubed plus 2x squared and y2 equals x squared plus 2x. So I took these questions, all these questions from a textbook, which I'll leave the titles below in the description box. Okay, so we want to get the area of the region bounded by both curves. Like I said, the top curve minus the bottom curve, but since we have a negative section, which is a pink section, we need to separate this and do two different integrals. So integral of from -2 to 0 of the top, which is y2, minus y1. How do I know which one is y2 and y1? You simply look at y2, which is the quadratic and is a parabola, right? And then y1 is the cubic function. It's quite easy to identify when you know how to do functions. Okay, this would be what our integration needs to look like, the pink and the green section. So let's do y2 and y1, simplify them so that we can plug them in there. So y2 minus y1 will give us x cubed plus x squared minus 2x. y1 minus y2 will give us the reverse of that, right? So it's going to be a negative value. So I'm just going to affix a negative value to it. But keep in mind, we must take the absolute values of these functions at the end of the day. Okay, so let's plug that in, integrate them by adding 1 to the power and dividing by the new power. Going to have x to the power 4 plus x cubed, x to the power 4 over 4 plus x cubed over 3 minus x squared from -2 to 0. And then the same function from 0 to 1. The same function with slight difference of a negative, of course. Don't get me wrong. Okay, so let's plug in our values. We have the pink area and the green area. You substitute all those numbers in there. That's a lot of fractions, and I know nobody likes fractions, especially students. So when you work that out, it should give you the absolute value of -2 minus 8/3 plus absolute value of -1/4 minus 1/3 plus 1. Okay, that gives us 14/3 plus 5, 12. Simplifying using a common denominator should give us 101/12 square units. Question 73. Find the area enclosed by y equal to y minus x and y squared equal to x plus 1. Here's what the graph looks like. You can plot this using decimals, and you would see that you would need to go with respect to y from what the shaded region looks like. So you need to make x the subject of the formula in each of these cases. So for the first one, x is 1 minus y, and for the second one, x is y squared minus 1. Okay, now which one is the top, or let's say the function ahead? It's the straight line, right? So you need to take the integral of the straight line and minus the integral of the curve, which is the parabola. So that will be x1 minus x2, starting from -2 to 1 according to the graph. We plug in each of the functions, we subtract and simplify, then we calculate absolute value. Simplifying that, means we need the integral of 2 minus y squared, and that will be 2y minus y squared over 2 minus y cubed over 3 from -2 to 1. Substituting 1 and -2, we should get 9/2. Question 74. The region in the first quadrant between f of x equal to 6 minus x squared and h of x equal to 8/x squared is rotated about the x-axis. Find the volume of the solid generated. Okay. We know that volume is the same as pi y squared dx, right? So we need to get our function y and square it up. So for two functions with which we want to find the integral, we need to take the top one, which is the yellow one, minus the green one, which is the bottom one. Just like so, we have the integral pi times the integral of the top one, f of x, minus the bottom one. You can as well just subtract them, get your new value of y, square it up before you get the integral. Okay, so f of x squared is 6 minus x squared all squared. When you expand this, you should have 36 minus 12x squared plus x to the power 4. H of x squared is 8/x squared all squared, and then doing that, you get 64/x to the power 4. So now we want to integrate each of these, which is still easy because you just need to add 1 to the powers and divide by the new powers so that you get this result. Now we need to substitute the limits, which are the x values from the curve. As you can see here, it starts from square root 2 to 2, right? So we're going to plug in square root 2, get the result, plug in the 2, and then minus each of them. We would have pi times 0.79, and that gives us 0.79 pi. Question 75. The region enclosed by the curve y equal to x parentheses x minus 2, and the x-axis is rotated through 360 degrees about the x-axis. Find the volume of the solid generated for y. Since volume is the same as pi y squared, we're going to square this value of y. This should give us x squared times x minus 2 all squared. Expanding the brackets and multiplying again by x squared, we'll get x to the power 4 minus 4x to the power 3 plus 4x to the power of 2. Integrating this, we would have x to the power 5 over 5 minus 4x to the power 4 over 4 plus 4x cubed over 3 plus c. Question 76. So we are now moving to the more advanced section of this video. So let's look at the last 25 questions. Integral of sec to the power 8x of dx. Okay. So for this, we would have to know that sec square x is important. So we separate this into sec square x and sec to the power 6x. Now, where am I going to with this? Sec square x is the same as tan square x. Don't forget that. Tan square x plus 1, pardon me. So we can rewrite this function as sec square x all cubed times sec square x. Okay, stay with me. Now, recall that sec square x is tan square x plus 1. Good. Now we're going to substitute this value into the equation. But what do we notice? If we were to take just tan x, right, as a different variable and we integrate and we differentiate it, it will give us sec square x dx, right? So sec square x is the derivative of, what's on the inside of the parentheses. So letting tan x be u, the derivative is sec squared. It means that this would be u squared plus 1 all cubed du. Using binomial expansion, or the binomial expansion formula, we would see that u squared plus 1 all cubed is the same as u squared cubed plus u squared all squared, and so on. Simplify that, we'll have u to the power 6 plus u to the power 4 plus u squared plus 2 plus 1, sorry. Okay, so it means we need to integrate this. We replace it in there, and then we can add 1 and divide by the new power. Easy peasy. Now we substitute u, which was tan x, and we should get our final answer. Let me know if you got this question right. It was an interesting one. Question 77, we have theta squared over cos theta cubed, d theta. Notice that the numerator is the derivative of the denominator, which has theta cubed. So we're going to let theta cubed to be u first, differentiate it, and then we substitute it into our equation, like so. It's going to be integral of theta squared over cos u times du over 2 theta squared, which will eventually cancel out. And then we're going to have half integral of 1 over cos u. I've done the integral of 1 over cos u, which is sec u, in a section in this video. Okay, remember we've done integral of 1 over cos u, right? So this would actually be cos u over cos u times cos u. That would make us cos u over cos squared u. You can use trigonometric identities of cos u right here, which is 1 minus sine squared u. If you let u or t, another variable to be equal to sine u, that will give you dt equal to cos u du. Keep in mind the cos u would cancel out once again. You would have the difference of 2 squares. We have done this in a part of this video, so I'm just going to go a lot faster. Like so. And then you integrate, you have a natural log. So you have natural log of t minus 1 over t plus 1. The value of t is sine u, but then what is u? U was theta cubed. So if you substitute that back again, you're going to have negative 1/4 natural log of sine theta cubed minus 1 over sine theta cubed plus 1. That's our final answer, plus the c. So we forgot the c. I am not a good pirate if that's the case. Question 78. We have the integral of 1 over 4x cubed plus 7x dx. Now we are going to rewrite this expression, which has 4x squared plus 7 as 2x all squared plus 7. We also need to factor out the 7 such that we would have 2x over square root 7 all squared, so that it goes back to normal. And then on the outside we have 1 over x over 7. Okay, replace that into our original equation, and then we let u be equal to 2x over 7, so that 7 du equal to 2 dx. Replacing these values, we'll have 7 over 2 du and 1 over x over 7 u squared plus 1. Okay, here we would need to use back substitution. What does that mean? Since we let u be equal to 2x over 7, it means that we need to make x the subject so that we can also replace it into the equation. You would see that it's going to be 7u over 2, and the 7 will eventually cancel out, right? So our new integral would be half integral of 1 over u over 2 times u squared plus 1. The 2 which was at the denominator goes to the top, and we have 2 over u times u squared plus 1. The 2 will cancel out, and we have 1 over u times u squared plus 1. Using partial fractions, we have a over u plus bu plus c over u squared plus 1. When we simplify, there's just the numerators, right? We have a into u squared plus 1 plus u times bu plus c equal to 1. We can actually substitute u equal to 0 so that we can calculate a. That gives us a 1, right? And then we'll substitute a 1 so that we have a times 2 plus b plus c equal to 1. Putting in the value for a, which is a 1, we have b plus c equals to -1, and let's call that equation number 1. Okay. We're going to have when u equal to -1, we do the same process, and we get a second equation. Now we have 1 and 2, we use elimination method to work out either of them, b or c, and we'll see that b is -1, while c is just a 0. Substituting the values of a, b, and c into our question, we'll have the integral of 1 over u plus integral of -1 over u squared plus 1, which is the tan inverse function, right? Okay, the first one is actually the logarithmic function, so we're going to have natural log of u minus tan inverse of u plus c. But remember, u was 2x over 7, so which will be natural log of 2x over 7 minus tan inverse of 2x over 7 plus c. That's our final answer. Question 79. We have 1 minus cos 3x over 1 plus cos 3x dx. Okay, interesting. You know that it's usually easy to integrate when you have just, let's say, cos 2x or cos x, right? Integral of cos 2x would actually be half sine 2x. But here we have 3, right? So let me show you a trick. We're going to use trigonometric identities. Remember, cos squared x is equal to half times 1 plus cos 2x, right? Okay, let's first of all try to get the identity for just cos x, right? So it means we're actually dividing by 2. So it means cos squared x over 2 will be equal to half 1 plus cos x. And then times by 3 means cos squared 3x over 2 is equal to 1 over 2 into 1 plus cos 3x, which is what we're looking for. Okay, this means 2 cos squared 3x over 2 is equal to 1 plus cos 3x. So similarly, sine 2 sine squared 3x over 2 will be the same as 1 minus sine 3x. Now we are going to substitute this into our equation. We have 2 sine square of theta, let's call it theta, over 2 cos square, which is tan squared. 2 cancels out, so this will be tan square of 3x over 2. Now, how do we integrate tan square x? Tan square x is the same as 6 square x minus 1, right? I'm just calling it an x because 3x over 2 is actually quite cumbersome to say all the time. So we have 6 square x, 3x over 2 minus 1. Replacing this in here, it's easier to replace with 6 squared because we know that the integral of 6 square x is just tan, right? So that will be tan of 3x over 2 minus x. Keep in mind, the angle is 3 over 2x, so we need to flip that over and multiply it by a factor of 2/3. So it will be 2/3 tan of 3x over 2 minus x as our final answer. Question 80. We have the integral of natural log of x squared plus 1. If we look at what's in the parentheses, we have x squared plus 1, right? If we differentiate that, you would have a 2x, but then there's no x attached to the question with which we can, easily substitute and cancel it out. So let's rewrite the question as 1 times natural log of x squared plus 1 dx, so that if we use integration by parts, when we integrate the 1, we're going to have an x to which we can affiliate the derivative of what's in the parentheses. Okay, so if u is natural log of x squared plus 1 and then dv is 1, that means v will be x and du by dx is 2x over x squared plus 1. Substituting these into the formula, we're going to have our integral being equal to x natural log of x squared plus 1 minus x times 2x over x squared plus 1. Okay, that's interesting. The numerator will come to x squared over x squared plus 1. And keep in mind, there's 2 ways we can simplify this polynomial fraction. We can use long division method because the degrees are the same. It's 2x squared and x squared in the denominator. You can use long division. You can actually rewrite this as 2x squared plus 2 minus 2, right? So that you can factor out 2. When you factor out the 2, we're going to have x squared plus 1 that will cancel out, and then we now separate each integral. So this would be 2 minus 2 over x squared plus 1. Okay, now if we was to integrate this, we're going to have 2x plus 2 tan inverse of x, and our final answer will be x ln x squared plus 1 minus 2x plus 2 tan inverse of x plus the c. Moving on to the next question. Question 81 says, integrate 1 over 1 minus x squared to the power 3 over 2. Again, when we see 1 minus x squared, we can think of 1 minus cos square x or 1 minus sine square x. So we let x equal to sine u, the x will be equal to cos u. Substitute that in there. We're going to have 1 minus sine square u, which is cos squared u, but then the squared will cancel out, and we're going to have cos cube u. So we're going to have 1 over cos cube u times cos u. One of them cancels out, and we have 1 over cos squared u, which is the same as the integral of sec squared u, which is great because that's just tan u. Okay, then u is sine inverse of x, so we have tan times sine inverse of x plus c. Question 82. We have the integral of 8x plus 13 over the square of 4x plus 7. Well, 13 can be written as 40 minus 1. Now we're going to factorize a 2 outside from each of them. That will give us 2 brackets 4x plus 7. Sorry if I use bracket and parentheses interchangeably, okay? They mean the same thing. So now we're going to separate each of them and give them denominators. And then the denominator of the first term can be written with the power of a half, like so. And since we can use the rule of indices here, we would have 1 minus a half for all of that term. 1 minus a half is still a half, so our first term is going to be the integral of 2 times 4x plus 7 to the power half minus 4x plus 7 to the power minus half, which is good. Over here, if we differentiate inside, we can see that it's going to be just a 4, but we don't have a 4 attached to the question. So what do? We can actually multiply by a 4 on the outside, like so, for each of them, but make sure we neutralize it by multiplying by a quarter on the outside as well, so that the outer part can be the derivative of the inner part. Okay, then we can now rewrite this integral, adding 1 to the power and dividing by the new power, like so. This will be 1/4 times 2 times, all of that expression. Okay, simplifying the expressions, you have 4x plus 7 to the power 3 over 2 times 3 minus 4x plus 7 to the power half over 2. Question 83 says we should integrate 0 to 2 pi e to the power ax cos bx. Interesting. Integration by parts would be used here, but it's tricky because we have not been given the values of a and b. Let's just let u to be e to the power x, ax and dv be cos bx, right? The derivative of e to the power ax is the same as ae to the power ax, while the integral of a v would just be 1 over b sine bx. Substituting that into our formula for integration by parts, we would have this value right here. Keep in mind we are just focusing more on the term which still has the integral attached to it, which is the last term in this equation. So I'm going to take out the constants like so and integrate these once more, okay? U being e to the power ax and dv being sine bx. When you differentiate, you have a e to the power ax and v equal to negative 1b cos bx. Substituting our values, which might look a little cumbersome, so you must take your time with these. You have e to the power ax sine bx over b and so on. Now, bringing out the parentheses and multiplying by the negative which was outside, we would have left over the integral of a squared e to the power ax cos bx over b squared. Now what do we notice here? This is similar to what we had in the beginning, so we might need to bring the like terms together. But first, we separate the constants like so. And then we can now see clearly that we have e to the power ax cos bx. So we're going to take it over to the left-hand side of the equation. And then we now factor out this integral. If we factor out this integral of e to the power ax cos bx dx, we would have 1 plus a squared over b squared in brackets. Good. And now on the right hand side, we have just the integral value. Well, we're going to first go ahead and substitute 0 to 2 pi, right? If we put 2 pi in here, we will get e to the power a 2 pi sine 2 pi b over b plus a over b squared e to the power a 2 pi cos 2 pi. We substitute the 0 as well, and then we subtract it from that. So when you substitute 0, you should get this value, which you would subtract from the first term. Okay, once you get that, do not forget the constant term that you had factorized on the left-hand side. So you're going to have this value, but make sure you divide all through by that constant term like so, to give us 1 over a squared plus b squared. Moving on, we have question 84. Integral from 1 over e to e of 1 minus ln x to the power 4 over x. So we're going to start by rewriting the ln x using our rules of logarithm. This will be 1 minus 4 ln x. And remember that ln x, its derivative is 1 over x, which is perfect. So if we focus on what's on the inside, right? 1 minus 4 ln x. Differentiating that, you have just 4 over ln over x, pardon me. So we need to take out a 4 as always, but we neutralize it with the 1/4 on the outside, like I always say, such that this can be rewritten as the integral of square root of 1 minus 4 ln x times 4 over x dx. Now you can better see the derivative function. When you see the derivative function, you just go ahead now to integrate what's on the inside of the square root by adding 1 to its power and dividing by the new power. So let's say that the value in the square root is u. You have root u, you integrate that, you have a new power of half plus 1, which is 3 over 2. Divide all through by that value, it gives you 1/4 times 2/3 times 1 minus 4 ln x cubed. Now we're going to substitute the values of e and 1 over e in there, and we'll get this 1 minus 4 ln e to the power 3 and 1 minus 4 ln e to the minus 1 to the power 3. Now the first part of it would have a negative value because 1 minus 4 is negative 3, and the second part will have a positive value, that's 5 cubed. And this should be our answer. Question 85. We have the integral from negative 7 to 7 of square root of 49 minus x squared dx. So we have two squares, difference of two squares, but we can actually factorize 49 such that it becomes 7 squared, and then you would have 49 into 1 minus x squared over 7 squared. Now that x squared over 7 squared is what we want to factor out on its own, so that it becomes 1 minus x over 7 all squared. Then we're going to let x over 7 to be any trigonometric identity. We can choose sine, so we let x over 7 be sine u, means the derivative is 7 cos u. And when we substitute in there, square root of 1 minus sine u is actually cos. So we're going to have the integral of cos u times cos u, cos squared u. Okay, use the identity again of cos squared u. That'll be integral of half times 1 minus cos 2 u du. Perfect. So our answer is 49 bracket x minus half sine 2u. Now, when x is equal to 7, u is sine inverse of 7 over 7, which is 90 degrees. And when x is negative 7, you have u, which is equal to sine inverse of minus 7 over 7. And that should be negative 90 degrees. Now, we can put our limits. Keep in mind, I changed the values of the limit of the integral to match up with the trigonometric functions, right? So now I'm going to put in 90 and negative 90, like so. We work that out, and we should get our answer 4,410. Cool. Question 86 is actually the integral of a piecewise function. F of x being equal to negative sine x when x is 0, and f of x being equal to 2x when x is greater than 0. So this would depend on our limits, right? So the limits go from negative pi to 2. Now negative pi is actually less than 0. So we need to break this up into two parts. We have the integral of negative sine x when it goes from negative pi to 0, and then the integral of 2x when it goes from 0 to 2. Okay, what's the integral of negative sine? It's actually cos x, and the integral of 2x is 2x squared over 2, which is just x squared, from 0 to 2 and from negative pi to 0. Substituting the values here, we have cos 0 minus cos negative pi plus negative 2 squared minus 0 squared. If we simplify all our answers, we should get a 6. Integral of negative 1 to 1, the square root of 1 minus x squared. So we have on the side a circle, the unit circle. Why is that shown? It's simply because this equation is the equation of the circle with radius 1. If you have x squared plus y squared equal to 1, then y will be 1 minus x squared, square root of 1 minus x squared. Okay, now when we're talking about the integral of the equation of the line, it means we're talking about the area it makes with the x-axis. Okay, so in this case, we can just use the area of a circle. Now, the integral of a circle is equal to the area of a circle, just as shown, which is pi radius squared. The radius is 1, so that is pi times 1 square. Okay, keep in mind we're taking the area it makes with a positive x-axis, so that just makes half of this circle. I'm going to shade it in so you see. So we're going to have to take pi times 1 square over 2, and our answer is pi over 2 square units. Okay, question 88. We have the integral of sine cube of x. So we can rewrite this as sine square x and sine x, right? And we can replace the value of sine square x as 1 minus cos 2x. Substituting this, we're going to have kind of a loop, I think. So we're going to have half into 1 minus cos 2x sine x dx. And when you expand the brackets, you would see that it's sine x minus sine x cos of 2x, which does not really help a lot, because if you substitute cos 2x again, which is sine square x, you go back to the original question. So let's forget about that, scratch that, and start with this. If we have sine cube x, right? Now, I just did this to show you how, as a student, you can try different methods to integrate. If one doesn't work, you cancel it out and you try it another way, okay? That's the reason why I put this up here in this question. So now we're going to do sine square x sine x once again. This time around, we're going to do sine square x being equal to 1 minus cos square x. Why are we doing so? We can identify cos at least in the function, right? So if we let another variable to be cos, it will be easier to cancel out because the derivative of cos is sine. So we substitute that in there, expand the brackets like so, integrate each of them. Now we're going to let u be equal to cos of x, which is the one with the higher power. The derivative is du over sine x, negative sine x. Then we substitute this in, it cancels out, and then we replace the value of cos x as u, then we integrate. This will be negative cos x plus u cubed over 3, and then replacing the u again, which was cos, we'll have negative cos x plus cos cubed x over 3 plus c. Question 89. So we have the integral of a floor function, which is interesting. The floor function, the floor value of x squared. So we need to find the integral from 2 to 4. So we're going to do this visually using its graph, okay? So if f of x is equal to x squared, what happens when x is 2? Since we're integrating from 2 to 4. When x is 2, we have 2 squared, which is 4. And the floor function of 4 will be all the numbers that are greater than 4 but not equal to, let's say, 5. So we're going to have 4.1, 4.2, because the floor values would still be 4, right? So it looks like this. That's when x equal to 2. Now, when x is equal to a 3, it's inclusive. When x is equal to a 3, we have 3 squared, which is 9. Floor value of 9 goes from all the numbers that are slightly greater than 3 but not up to 4. So 3.1 squared will give you a number that is close to 9 but not greater than 9. Then you do the same thing again. When x is equal to 4, you have f of x being equal to 16. Floor value of 16. Okay, let's say do f of x equal to 4.1 and you square it. It will still give you a function that's close to 16. So the floor function of that value would still be 16. And now you have the graph. But now remember, integration is actually the area on the graph, like combined together. So what we're going to do is calculate the area of each of these rectangles. In this case, we're going to have 4 plus 9 plus 16, which will give us 29. And that's how you can calculate this area. Question 9t. Okay, we have the integral of x cubed ln x dx. So with this, we're going to take dv to be x cubed. So in that case, its derivative is 1 over x, and v is x to the power 4 over 4. Replace into the formula for integration by parts, we would have x to the power 4 over 4 ln x minus the integral of x to the power 4 times 1 over 4 times x. Now some of the x's will cancel out nice and neatly. We're going to have x cubed over 4, and to integrate x cubed over 4 is not hard. It will just be x to the power 4 over 4, which multiplies to give us 16. So our answer is x to the power 4 over 4 ln x minus x to the power 4 over 16. 10 more questions to go. We have the integral of x sec x tan x dx. It will let u to be x and dv be sec x tan x. The derivative of x is 1, but then the integral of sec x tan x has to be worked out. So remember that the derivative of sec x is equal to sec x tan x. So if you integrate sec x tan x, you should actually just get sec x, just like this. So it means we can just replace this into our question right here and change this to sec x, and that gives us our final answer. You can actually factorize the sec x if you want to make this look simpler and include the c. Question 92, we have 1 plus tan x over 1 minus tan x dx. So tan x is the same as sine over cos, right? So if you simplify this sine over cos with denominators as cos would actually cancel out. In the numerator, we're going to have cos x plus sine x, and in the denominator, we're going to have cos x minus sine x. Now, looking keenly, the numerator is actually the derivative of the denominator. The only thing is the positions have been interchanged. So, the numerator can be written as sine cos x plus sine x, while the denominator we have cos x minus sine x. So, when you're integrating a function with its derivative as part of that question, you will just simply have natural log of cos x minus sine x plus the c. Question 93, we have 1 over x to the power 4 plus x. So we can factor out the x to the power 4, and this is going to be 1 plus x to the power 3. Okay. Now this gets interesting because you can just actually find the derivative without necessarily using partial fractions. So if you look keenly, the derivative of 1 over x cubed is actually 1 over negative 1 over x to the power 4. If I rewrite this equation like so, it will be 1 over x to the power 4 into 1 plus x to the power negative 3. Shift this to the right hand side. We see that this is actually the negative of the derivative that we need. So I'm going to neutralize it with the negative on the outside as well. Once again, it means that this will be the natural negative of natural log of 1 plus x to the power minus 3 plus c. Question 94. The diagram shows the curve y equal to half x minus 2 all to the power 6 plus 5. Find the area of the shaded region. So when x is equal to 0, y is equal to 69. It means that this graph cuts at 0, 69. So the straight line which is at the top of the graph is actually y equal to 69. So now that we know that's the top function, and we also know the bottom function, we're going to subtract the bottom from the top. Also, we need the second point that intercepts with the line y equal to 69. So when y is equal to 69, x would be equal to 8. It means that we need to take the integral from 0 to 8 of this function. So 0 to 8 of y1 minus y2 dx. Now if y1 is equal to 69 and that's y2, we need to subtract the both of them and work out their integrals. So this would be 69 minus 5, which is 64 times half x minus 2 to the power 6. Integrating this, we can separate both expressions like so. And then we can see that the derivative of what's inside the bracket will just be a half. So to neutralize this once again, we'll multiply by half, but then multiply by 2, okay? So that it cancels out. And then what's on the inside with its power, which is to the power 6, can now be integrated as usual. So we add 1 and divide by the new power. Now, this would be 64x minus half x minus 1 to the power 6 plus 1 over 6 plus 1, which is basically 7. Okay, don't forget to multiply by the 2. If we simplify the fraction, we should get this, but we must substitute its limits. So from 0 to 8, we put in 8, find the value, and put in 0 as well, find the value. Then we subtract to have our final answer, which is 3072 over 7 units. Question 95. We have the absolute value of 1 minus e to the power x minus 1. Now this question is different. We can do it two ways. We need to get the absolute value function of the function itself. So when it's negative and when it's positive. So case 1, when x is greater than 0, what do we have? We have the function 1 minus e to the power x minus 1 dx. Integrating 1 gives us x, and integrating e to the power x minus 1 gives us e to the power x minus 1, right? Plus c. That's the first case. And case number 2, when x is less than 0, we would have the negative of this function, which is negative 1 times e to the power x minus 1. This gives us the integral, which is negative x plus e to the power x minus 1 plus c. Question 96. The diagram shows the curve y equal to x cubed. The point P has coordinates 3 and 27. And PQ is the tangent to the curve at P. Find the area of the region enclosed between the curve PQ and the x-axis. So if this line is tangent to the curve at P, right? Touches just at one point, it means that it will have the same derivative. So we need to integrate y with respect to x and substitute the values for P at that point. So dy by dx is 3x squared. Now at x equal to 3, we'll have 3 times 3 squared, which is 27. Now that's the gradient. At least you have a point through which the straight line passes through. So remember the equation of straight line is y equal to mx plus c. And at point 3, 27, we will have 27 equal to 27 times 3 plus c. And c is negative 54. Now we can get our final integral. We need to get the area of the region enclosed between the curve. We're going to have to subtract y1 and y2, given that y1 is the curve and y2 is the straight line. So we have the integral of x cubed minus 3x minus 54 from 0 to 3. That would be x to the power 4 over 4 minus 3x to the power 2 over 2 plus 54x. From 0 to 3 means we plug in 3 in there, like so. Plug in 0 as well, and we work it out, practically. This will give us our final answer, which is 168 square units. Question 97. Find the volume of the solid revolution obtained by rotating this region about the x-axis. Y equal to x sine 3x for pi less than x less than pi over 3. Okay, for volume of integration, remember we need to do the integral of pi y squared. So we must square this y before plugging in the formula. That will be 0 to the pi over 3 of pi x sine 3x all squared. Good. So if we expand the brackets, this is going to give us the integral of pi x squared sine squared 3x. Now, sine squared x is equal to half minus 1. Half into 1 minus cos 2x. So what would be 3? We use the same tactic that we did before by multiplying this equation by 3, which would be half into 1 minus cos 6x. Now we have the integral from 0 to pi over 3 of pi x squared times half times 1 minus cos 6x. If we take out the constant, we have 1 over 2 pi, then x squared times 1 minus cos 6x. If we expand the brackets, we're going to have the integral of x squared minus x squared cos 6x, right? Now, the problem will be to work out the integral of x squared cos of 6x. We would need to let u be x squared and dv be cos 6x, which is integration by part. Differentiate, but I think this time around we need to differentiate twice to get rid of the x completely. So differentiate that, we will have 2x equals, we'll have the du by dx equal to 2x and v equal to 1/6 sine of 6x. Now our volume is half pi from 0 to pi over 3. So if this is our equation that we're trying to integrate, we replace each of the values. We'll have x cubed over 3 minus x squared sine 6x over 6 plus integral of 2x over 6 sine 6x. Once again, we can still take u to be equal to x, dv equal to sine of 6x. If u is x, then du will be 1. And if dv is sine 6x, therefore v would be negative 1/6 cos of 6x. Okay, substituting these into the right hand side of the equation, we're going to have our new integral. 2/6 of x sine x is actually 2/6 of x negative x over 6 minus cos 6x over 6. So we're going to replace this value that we got into our equation right over here, such that we have the volume being equal to half pi x cubed over 3 minus x squared sine 6x over 6 plus 2 x sine 6x dx. Now our final answer would be 1 over 2 pi x cubed and so on plus c. Okay. Question 98. The region between the curve y equal to pi x squared, the y-axis, and the lines y equal to 2 and y equal to 5 is rotated through 360 degrees about the y-axis. Find the volume of revolution which is formed. So again, it has been rotated through the y-axis, pi x squared dy, so with respect to y as y is changing. From here, it's easy to make x squared the subject of the formula, which is just pi y over pi. Then we integrate this value with respect to y. We're going to have y squared over 2 times pi. Now from 2 to 5, we can substitute 5 and 2 in there. We're going to get 21 over 2. Question 99. We have the ellipse width equation. X squared over a squared plus y squared over b squared is equal to 1. And the diagram has semi-axis A and B. Deduce the volume of the ellipsoid form if the ellipse is rotated about the y-axis. So if the ellipse is rotated about the y-axis, it means we will need to take from negative b to b, or better still, we can take from 0 to b and then multiply by 2 later. So now here's the value of x squared. If we substitute it into that formula, we have integral from negative b to b of a squared times 1 minus y squared over 2b squared dy. And like I said, we're taking half of it, so from 0 to b, and then we'll multiply by 2. For us to integrate with respect to y, we're going to have y cubed over 3 times the b squared that already exists. And when we integrate 1, we have y. This all goes from 0 to b, so we need to plug in the values of 0, which would definitely cancel out, while b would still be there. So we're going to have 2a squared times b minus b cubed over 3b squared. And if each of the b squares cancels out, we're going to have 1 left over. So here we're going to have b minus b over 3. And then finally, we have 2a squared times 2b over 3. Now we can finalize our answer and say that this is going to be 4a squared b over 3. Now we're getting this so that we can use this in question 100. Which says we should calculate the volume of the solid revolution when the ellipse with equation 4x squared plus 9y squared is equal to 36 is rotated about the line y equal to 5. Okay, this is about a line, so we need to be able to visualize this as well. The ellipse equation has not been given a standard form, so we need to standardize that by dividing all through by 36. All right, so we divide all through by 36 like so. This would be x squared over 9 plus y squared over 4 equal to 1. Okay, now we have written our equation in standard form of an ellipse, and we can visualize this over here using even Desmos. So we have the line y equal to 5 at the top, and we have the ellipse at the bottom. Now for ellipses, the volume of the solid of the revolution form is 2 pi from arrow of A to arrow B, RH dr. If you look keenly, it's going to be like 2 pi RH, which is actually the volume of a cylinder, isn't it? So how so? If we rotate this, you're going to see that it forms a cylinder which is like flat, like horizontally lying down, right? Now we have the distance r, which is the radius of the cylinder, and then we have the height of the cylinder, which are actually tiny pieces of the ellipse, which can be integrated or summed up to form the integral that we need. Okay, so it's rotated about the line y minus 5. So we need to actually calculate just the distance from y equal to 5 and from any other value of the curve. So let's take x and y to be any point on the ellipse, right? Then 5 minus y would give us the r that we need, and the height that we need would be twice as much as x. So twice as much because we consider the left and the right hand side. So in this case, we can now integrate the function 2 pi from r of a to r of b times 5 minus y times 2x dr. So according to this, we might need the value for x so that we can substitute it in there. So x is equal to square root of 9 brackets 1 minus y squared over 4, which is equal to 3 square root of 1 minus y squared over 2 squared. So now we're going to plug it into our formula. Since dr is the same as dy according to the picture you just saw, we needed the value of x. So now substituting x there into our equation would make it look like this, so that we can later on expand and work it out. Okay, let's expand this. We're going to have 2 times 3, which is 6. 6 times 2 is 12 pi. And then we have 5 minus y times all of this in the square root. Taking each of them, multiplying by 5 and y using the FOIL method, this will be the integral of 5 times square root of 1 minus y squared over 2 squared minus the integral of y times the square root of y squared over 2 squared. Now for the second part, or the last part of this integral, which I just mentioned, notice that the derivative of y squared over 2 squared is actually y, which is good, which is already attached to the question itself. So that will be helpful for us. So we can now integrate. So the first part, which is the square root of 1 minus y over 2 all squared, is actually the same as integrating using the sign trigonometric identity. So let's take a look. For the first part, we have the integral from negative 2 to 2 of 5 times 1 minus y over 2 all squared, which we've done before. That will be 5 times sine inverse of y over 2 plus half times sine times 2 times sine inverse of y over 2. Okay, you can calculate this by yourself because we've done a lot of questions and examples in these previous questions. Now, if we substitute from negative 2 to 2, it will just give us 5 pi. Okay, for the second part of the integral, we want to get the value of the integral of y times square root 1 minus y over 2 all squared. So we use substitution like I said, or you just use the notion of the derivative being part of the question itself, and you should get your answer, which is negative 4/3 times 1 minus y squared over 4, all raised to the power 3 over 2. Remember, it's 3 over 2 because we had to add 1 to the power and divide by that new power. Okay, substituting negative 2 and 2, we should get 1.97. And hence our volume would be the difference between these two values, which are 5 pi minus 1.987, all multiplied by 12 pi, of course, which gives us 6 pi squared minus 23.73 cubic units. Okay, if you have any questions regarding this last segment, you let me know in the comment section down below. I'm going to explain further in another video. The last part of this video would be for you to work out this random question, which is the integral from 0 to infinity of x to the power negative 0.99. And you tell me your answer down in the comment section. That was it for this video. We've done 101 integral. If you found this video helpful in any way, you give me a thumbs up, or you can share with your friend who might need help with revising integrals. There were a few mistakes here and there which I figure out along the way, but that's fine. Integrating requires a lot of knowledge on differentiation, so I will be coming up with another video on differentiation which might help you understand this video better. And look out for 100 derivatives as well. I'll see you in my next video. Thank you.